I'm going to try and move a little quickly today so that we can get through the most important stuff before our folks need to leave for the assembly today. So I'm just going to ask that we pause on the side conversations. If you do have questions, go ahead and raise your hand. I might ask you to put a star next to it, and we'll come back to it, though. Okay? So here we go. We're talking about functions and their properties. Our first goal is to be able to look at a relation and answer the question, is it a function? So is y a function of x? The rule for a function is that each input must have at most one output. Or another way to say that is an input cannot have more than one output. So if we want to check to see if y equals 2x is a function, by its definition, we need to ask ourselves, if I take a value for x, and let's just pick a random number here, 3, if I take 3 and I plug it into this equation, I would get an output of y equals 2 times 3, or y equals 6. Is there any way I could ever get an output other than 6 by putting in the same input? No. Can you think of any special numbers that I could put into this that would give me two different outputs? That's not possible. So for every input, there's only one output, right? So I'm going to write each input has only one output, therefore it's a function. Each input has only one output, therefore it's a function. Wow. My handwriting got really bad over the summer. Sorry, it'll come around a little bit. It's not great. If you ever need me to translate anything that I've written up here, please ask. This is trying its best to say each input has only one output, therefore it's a function. What about this second one? Are there any values of x that would give you more than one possible output? I can think of quite a few. Can someone give me one concrete example? All we need to do is find one example to show it's not a function. X equals 0. I love it. 0, 1, -1. Those are always great things to try. Those are kind of where the weird stuff happens in math. So if x is 0, and I go to plug that in, y would be 0 plus or minus 1, which means sometimes y is 1, and sometimes y is -1. So we found an input that gave us two different outputs, so that's it. That's enough. We only need to find one example. There's a heck of a lot more than one, but we have one input, x equals 0, with more than one output. So not a function. All right. These next two are a little bit trickier because they're not y equals equation, they're x equals equation, but it's kind of the same idea. X is still the input, y is still the output for these. Someone give me a value of x. We've used 3, we've used 0. Give me something else. 7. X equals 7. So if x equals 7, let's figure out what y would equal. So I'd have 7 equals 3y. We do a little bit of algebra on that. And that gives us y equals, if I divide both sides by 3, I'd have 7/3. So we put an input of 7 in, and y ended up solving for 7/3. Is y ever going to be anything other than 7/3 with an input of 7? Can you think of any weird numbers that we could put in for x, where sometimes we're going to solve and get one answer, and sometimes we're going to solve and get another answer? Nope, I can't either. I can think of some values for, nope, actually I can't. Never mind. Take that back. So I would say it's a function. It's a function, yep. So I'm not going to copy this down again, but it's the same same reason. So it's a function. Hey. All right, part D. Pick a good one here. I want a nice clean value of y when we solve this. 2? I like 2. 8? 8 could work too. I'm gonna go with 2. So let's let x equals 2. If I make that happen, I got 2 equals y squared plus 1. And I'm going to solve that for y and see what I get. Now, if I get 2 possibilities, it's not a function. Minus 1 on both sides, we get y squared equals 1. Square root on both sides. What do we got to remember to do when we square root both sides? Plus or minus. So plus or minus 1 for y, therefore, not a function. All right, we have a single input 2 that could result in a 1 or could result in a negative 1. So this is not a function. Wah, wah, wah. All right. So that's the algebraic way for checking if something is a function or not. You all know the graphical one, right? Oh, I hope that's not a phone. So this would be a warning. Don't let me see it again, because we will take them this week. Yeah. Well, they won't. They'll just come and get it first thing Monday morning. Okay, here we go. You all know how to check if a graph is a function, right? Vertical line test, we learned that back in Algebra 1. I'm not going to review that again. If that's not ringing a bell, do a quick Google search and remind yourself how that works. My assumption is that you guys know that domain goes with x or input values and range goes with y or output values. Yes? We're comfortable, familiar with that? All right, our next goal then is to find domain algebraically. There's a lot of words right here. I'm not going to read through them, and I would encourage you to just listen to my Cliff Note version. I'm going to give you sort of the short version of this. Now, finding domain algebraically, the way we're going to do this is we're going to look through our function to see if there are any parts that have input restrictions. Guys, I'm going to ask you to pause your side conversations, please. Thank you. We're going to see if we have anything with input restrictions, okay? And these are special components or pieces of functions that could cause problems. And for right now, there's really only 2 that we got to worry about. You guys have learned in algebra that there's a rule about division in algebra. What could screw stuff up if we divide by the wrong thing? What can we not divide by? We can never divide by 0, okay? So any function that has a fraction in it has a possibility of breaking, because if you end up with a 0 on the bottom of that fraction, we're not going to be able to evaluate it, okay? So any fraction that we see in our function has the restriction that the denominator cannot be equal to 0. The other thing that we got to worry about is square roots, and actually 4th roots and 6th roots, because what are we not allowed to have underneath a square root if we want to deal with real functions? We can't have negatives, right? So we know the rules that we cannot divide by 0 and we cannot have a negative inside of a radical. We actually need to shift our thinking, though, because our goal is to find the domain, what we are allowed to do. So we're going to look at the opposites of those 2 things. We're going to say what must be true about those 2 things. So we're going to find these things. We're going to write an inequality based on the restriction. And then we're going to solve that inequality, and that inequality is going to tell us the domain. I want you guys to keep in mind what the domain is. The domain is the list of everything that can go into the function, right? It's any number that can go in without screwing anything up and making the function break. All right, so here we are. We're going to work through a couple examples with rational functions. And the restriction for a rational function is that the denominator must be not equal to 0. Which is kind of strange to say in English, but that's how we want to do it mathematically. We're not going to say the denominator can't be 0. We're going to say it must be not equal to 0. As long as we make sure that the denominator is not equal to 0, then we're good to go. So let's look at this first example. I'm looking through here. I see a fraction. My eyes go immediately to this denominator, x minus 1. I'm going to take that thing that's in the bottom, that's the part that has the restriction, I'm going to rewrite it and I'm going to apply the rule to it. This fraction is going to be just fine as long as x minus 1 is not equal to 0. We're going to write that restriction. Now, some of you might be saying, why do we need to write that down? I already know what the domain of this is. It's everything except for 1. Okay, we're starting with an easy example. I want you to write it down because trust me when I say things are going to get trickier than this. Okay, so x minus 1 is not equal to 0, and then we'll use our powers of algebra to solve this inequality. So same way you would solve an equation, add 1 to both sides, we get x not equal to 1. And that's our domain. That was the only part of this function that had any restrictions. Now we know what the restriction on 1 is. We are good to go as long as x is not equal to 1. Let's go ahead and write this domain in interval notation. So when I do this, this part's not required, but it's really helpful to me. I like to make a number line. And I'm going to put any of the important numbers on the number line. The only one that's really important for this problem is 1. And how do I graph x not equal to 1? Well, really that means everything except for 1. That's my domain. So the domain of this function would be, and we practiced interval notation on Wednesday, so I'm going to kind of go through this part quickly, but I'll pause for questions. And we're finished. Why, yeah, it should be 1. Why did I write 0 there? I saw the little dot. Thank you. Hey, all right. Don't worry, that's only my 17th mistake of the day. Thank you. All right, other questions? Thank you, thank you. All right, let's keep going. This next function has 2 rational portions to it, so we're going to have a couple different restrictions. We're going to treat it the same way we did the last one, so we'll focus on them one piece at a time. I've got x plus 1 is a denominator. The rule for any denominator is that whatever that thing is that's in there must be not equal to 0. And we'll come back and solve that in a moment, but let's go ahead and take care of the other rational portion as well. This one has a denominator of x squared minus 4. And again, that restriction for denominators is they must be not equal to 0. We'll solve these 2 inequalities, and that will give us the restrictions for our domain. So I'm coming up with x cannot be -1, and it can't be 2, and it can't be -2. Is that what you guys are coming up with? Awesome. So let's make a little number line and put some open dots at those spots and write interval notation, and I'll try not to screw this one up. I need to put these numbers in order. -2 would be the smallest, then -1, and then 2. So we're looking at 1, 2, 3, 4 intervals this time. How many of you are going to have to leave at 1 o'clock? Okay. Or 1:15. Some people are at 1, some are at 1:15. Okay. Okay. Thank you. We're going to do a seating chart later, but I'll just have the folks that are staying here to remind me where people were sitting who left. So, okay. Are we feeling okay about the domain so far? All right, I got a question for you. Remember, it's important, we got the steps down, but what are we doing here? We're coming up with a list of everything that's allowed to go into this function. So I'm going to show you a domain for a function without showing you the function. And I'm going to ask you a couple questions about this, and we'll see if we're understanding. This is not necessarily a rational function. So I haven't given you the equation or the graph. I'm just telling you the domain. Can I? My question to you is, can I put 0 into this function and get an output? Can 0 go into this function? Is 0 part of that domain? Would 0 fall in this interval or in this interval? No. So 0, that means 0 would not go into this function. Okay, what about 5? 5 would work. So I could put 5 into this function. What about 3? No. Not 3. What about 3.00001? That would work, but not 3, right? So almost all the way to down to 3, but not quite. What about -2? Yes, -2 would be okay. What about -2.00001? Yes, -2.00001 would be okay. That's in here. I tricked you. What about -1.999999999? That'd be a no. Okay. So when we're making this, we're making a list of what can and can go in there. And in this case, it's actually easier to say what cannot. All right. What was the rule about what's allowed to be inside of square roots again, and fourth roots and sixth? Positives and not negatives. What's the one number that's not positive or negative? 0. 0 is okay for square roots, right? We can take the square root of 0. Yeah, it's just 0. So that means the inside must be greater than 0 or equal to 0. So when we're dealing with anything with an even numbered root, we take the radicand, whatever is inside of the radical, and the restriction on that is that it has to be greater than or equal to 0. As long as it's greater than or equal to 0, it's not going to end up giving us imaginary numbers, which would break our function. So if I want to know what x values are okay to put into this function, I'm going to look at it. I'm going to notice that it has an even root in it. I'm going to focus my attention on what's inside that even root, and I'm going to apply this restriction to it. So we have 1 minus 2x. And the restriction on radicands is that whatever it is must be greater than or equal to 0. As long as we keep it greater than or equal to 0, then we're going to be able to evaluate it and get an output. So let's solve this. Subtract 1 from both sides. Ooh, what's that thing we got to remember to do with? Yeah, we're going to end up flipping that when we divide on both sides by -2. Remember, with an inequality, anytime you multiply both sides or divide both sides by a negative, you have to flip the sign. It's going to be 1/2. You know what? I would feel better if I actually showed this step. I don't usually, but for some reason I'm losing my confidence in my... Yeah, I think that's good. I think that works. So what do we figure out? As long as we can make sure that x is smaller than 1/2 or equal to 1/2, then we should be good to go. We should be able to put any of those x values in, and we'll get an output. Sound good? Can you write that for me in interval notation? If you can jump straight to interval notation for that, go ahead. I'm going to go ahead and draw the graph. It's my fallback plan. It just makes me feel more confident. My important value here is 1/2. This has the little bar, so I'm going to do a solid dot at 1/2. And we shade where x is. X is allowed to be smaller than 1/2. So there's my interval. There's only one. So my domain in interval notation would look like that. or equal to. A half should be good as well. So it could be smaller than a half or equal to a half. So can I put 0 into this function? Would that cause any issues? We can put 0 into this function. Could I put 10 into this function? No. Could I put -1 into this function? All right. We get the idea. Let's do one more here. Oh, this one's fun. It's in a fourth root this time. Oh, and it's a quadratic. Hooray. Yay. X squared minus 25. Well, let's write our inequality. Now, I am going to insist when you do this on your test, and I would like you to practice it when you're doing your assignments as well. I want to see this step where you're taking the thing as it is inside of here and writing it with the inequality, with the restriction. I don't want you to take something like this and jump straight from this to x not equal to 1. I want to see this step, okay? This is really important. I want you getting in the habit of doing that so that when we get into some more complex later stuff, you got the skills you need. Okay, so let's do this. So write out the thing that is in the restricted part of the function, and then write the inequality part for your restriction. Anything that's inside of an even root must be greater than or equal to 0. And we're going to solve that. Now, I don't know if you guys remember solving quadratic inequalities last year or not, but I know that you did. Usually my students do not remember it because it's like a really quick thing. We're actually going to spend some time on it, and I think it's in the second chapter. For right now, I'm actually going to solve this inequality graphically, okay? You guys know what I mean by solving it graphically? I'm going to draw a picture of x squared minus 25, and I'm going to look at where that picture of x squared minus 25 is bigger than or equal to 0. I'm going to look at it, okay? Now, x squared minus 25 is one of those things that you all should be able to graph, like quick. So make a rough sketch of it off to the side here. What I'm graphing here is y equals x squared minus 25. Oops, you can't see that. I'm just going to make a rough graph of this. We don't need graph paper or anything like that. Tell me, where's my y-intercept? -25, it's down here, right here. And we know it's a parabola. It's going to open upwards. Can you tell me where it's going to cross the x-axis? At 5 and -5, right? We could factor this in x plus 5, x minus 5. So I need you to kind of be at the point that we can make that graph pretty quickly, okay? That's what this looks like. That's not what this looks like, okay? And this is where, in this class, we're going to be using pieces that you've already learned as a small tool in a bigger picture. So it's good to keep in mind what we're doing here. I'm not making a graph of my function. I'm not making a graph of this fourth root function. I'm just making a graph of the part that's inside of the square root. And why am I doing this? Because I need to know what values of x are going to keep this thing going, not break that. So if I'm looking for where this is greater than or equal to 0, where is it greater than or equal to 0? I'd say it's greater than or equal to 0 right there and over here, and it's equal to 0 right here and right here. I would say the solution to this would be from, well, I got -5 and 5, so I'm drawing my number line. I would say we are including -5 and we're including 5, and we've got all of these values and all of these values. All right, I want to just pause for a second and go back and make sure that we're all good with what we did here. Are we okay with how we wrote this inequality? Because that's just the rule, right? Whatever's inside the radical's got to be greater than or equal to 0. And then we have to solve this. Now, I'm going to tell you, if your plan on solving this was to add 25 to both sides and take a square root, you can't do that. That does not work for inequalities. I'm sorry, it just doesn't. It works for linear equations or inequalities, but it doesn't work for anything, any quadratics or cubics or anything like that. So if this had been like 2x plus 5 greater than or equal to 0, then sure, get the x by itself, all good. But as soon as it's a quadratic, you can't just get the x by itself by adding and subtracting and taking square roots. It just doesn't work. It doesn't work. There is a method for doing it. I'm going to show you later on, okay? It involves making a sign chart, if you guys remember making those charts with the little pluses and minuses. That sounds totally foreign, I'm going to teach it as if you've never seen it before when we get to it. But for right now, the way we chose to solve this is we're just going to graph y equals x squared minus 25, and we're going to look at where is it above the x-axis, right? Because that's what we're looking for. This is what we practiced on Wednesday. This is the solution to this, which means this is our domain. So I'm going to go ahead and write this in interval notation. Negative infinity to negative 5, and 5 to infinity. Now, a couple of you are going to have to leave right now. I'm going to just give you a synopsis of what you're going to miss. Those of you who are sticking around, just pause for a second. We're going to do one more problem today. It's just E. Can I get you to please stop talking for just a second so that those who are leaving can focus? This is a big old messy function. We're going to have multiple restrictions going on at the same time. We're going to treat them all separately, and we're going to make graphs of them and stack those graphs on top of them. So those line graphs like we just did, except we're going to have like 4 of them. I think 3 of them. We're going to stack them on top of each other and look for where all of those graphs overlap, and that will be our overall domain, okay? So we're just combining together what we just did here, except instead of one of these things, I'm going to have like 3 or 4 of these graphs that will stack on top of each other, and we'll look for where they overlap, okay? That's what you're going to miss. I'm recording right now. Just scrub to the end of the video and watch it. It'll make a lot more sense when you see it. All right, the rest of you guys, we're going to do this. Shh. Some of you are still here for another 15 minutes. If that's the case, please don't leave. If your neighbor is leaving, please make sure you know their name so you can help me with the seating chart here in a little bit, okay? All right, guys, let's do this quietly because I want to keep moving. Shh. If you're going, exit quietly so that the folks who are staying can pay attention because I'm not stopping. Okay, here we go. We got this wonderful looking function. This is going to be about as hard as difficult a problem as you see in this class. Okay, you won't even see anything this challenging on your assignments, let alone the tests. But let's just do something tough and show that if we just kind of keep in mind the basic principles that we talked about and put them all together, that this isn't that terribly difficult. Okay. So here we go. Start looking through here and tell me, do you see any? Let's start with rational. Do you see any fractions in this thing? Yes, me too. I see a fraction also. So we're going to have to deal with that. Go ahead and draw me a box around your denominator, the entire denominator of the fraction, because that's what the restriction is on. The restriction is on denominators of fractions. And go ahead and copy that. I'm going to put mine kind of right underneath here. And just copy it as exactly as it looks. And can someone please remind me, what is the restriction on denominators of fractions? They must always be what? Not 0. So take that denominator as it was and write not equal to 0. Now, I am not bothered at all by the fact that there's a square root inside of that denominator because I'm not even thinking about the square root right now. We're going to come to it. We're going to get to it in a minute. We're just dealing with the denominator right now, okay? We're going to trust that if we just keep everything kind of compartmentalized, follow the mathematical principles, that this is all going to turn out fine. Okay, so we need to solve this now. All right. Have you ever solved anything like this? Maybe not. Have you ever solved an equation where it was equal to 0 and you had two things being multiplied together equal to 0? You've done that like thousands of times, at least hundreds of times. What did you do with the two things that were being multiplied together equal to 0? What I'm saying is, like, if I had given you an equation like x plus 1 times x minus 3 equal to 0, how would you solve that? No, you wouldn't FOIL that. I mean, you could, but that's way more complicated than you need to. Yeah, you'd split it up and make two equations out of it. This is called the zero product property, right? And Who here has made the mistake of trying to do this when it wasn't a 0, when it was like a 5 over here, and you tried to say x plus 1 equals 5 and x minus 3 equals 5? Anybody ever made that? That's the classic mistake. This only works when it's equal to 0, by the way. Okay? And lucky for us, it also works when it's not equal to 0. So if I have two things being multiplied together, equal to or not equal to 0, I'm allowed to split them up and make two separate equations. So go ahead and do that. Except instead of them each being equal to 0, they're going to be not equal to 0. So you'll have x minus 1 not equal to 0, and you'll have the square root of x plus 3 not equal to 0. We're just using the zero product property. It works anytime you have multiple things being multiplied together. That's the product and the name. And it has to be equal to 0. That's why it's the zero product property and not the 5 product property. Is Kennedy here? Oh, she left. And she went to the assembly, so she's on her way. Thanks. All right, solve those for me. This one's easy. Actually, they're both not too bad. We could square both sides and get rid of this square root, right? How are we feeling? -3, yes, thank you. All right, now how are we feeling? That's bothering me. Hang on. Okay, so far so good. We got more work to do, but have we taken care of the denominator? Yes, question. I'm not, right now we're dealing with denominators, and the rule for denominators doesn't have anything to do with less than or greater than. Okay, so I love your question, but can we wait until we get to square roots? I have not, my brain is completely focused on denominators right now. Now this denominator happens to have a square root in it, but I'm not thinking about, that's just, to me right now, that's just like happenstance. So you did ask a very good question, and we're going to come back to it though. Thank you for that. All right, other questions before we move on? All right, now let's deal with roots. Do you see any even roots? There's 3 roots in this thing. I see 2 that we're going to have to worry about. There are no restrictions on odd-numbered roots. You can have positives, you can have negatives. It's okay. Okay, so this can be anything. We don't have to worry about this, but we do have. We got a root, even root here. It's got a 2 minus x as the radicand. And now that we're talking about roots, can you remind me what's the restriction on radicands? Can't be less than 0, or it must be greater than or equal to 0. So this works a lot better if you think of it as what must it be rather than what it can't be. So we are going to insist that whatever 2 minus x is, it must be greater than or equal to 0. Remember, we're looking for what we can put into this function, not what we can't put into it. So focus on what it must be rather than what it can't be. Okay, we'll come back and solve that in a minute. Are there any other roots that we need to worry about? Yes, even though it was part of our denominator, it is also a root, so we're going to also need a restriction for x plus 3. So x plus 3, since it is inside of an even root, must also be greater than or equal to 0. So we'll go ahead and solve these, simplify them down so we can just get a single x on one side. Do your algebra here. Okay. -3, thank you. I keep leaving that negative off. What is going on today? Long week. I did warn you guys you're going to see me make like 1,000 mistakes in this class, right? What's that? Oh, it's talking and writing at the same time. Plus, I'm an old guy. you know. So we're kind of starting to get around to your question a minute ago, right? You were asking about can't X also not be, so right now are you kind of making a connection of how we're gonna sort of resolve and come back to what you were saying a second ago? All right, now what I need you guys to understand, again, remember this is where we want to make sure, like, can we do these steps? That yes, I'm feeling pretty confident that we can do the steps. Do we know what we're doing? Let's always keep that in mind. What is going on here? Our ultimate goal is to find a rule for the x's that are allowed to go into this big weird function. Okay, that's our ultimate goal. I want a rule that says as long as x follows this rule, then it's okay to stick in there. All right, so we started with the things that could potentially cause us problems. We started with the denominator, and we came up with a couple facts about x that must be true in order for it to go into this function. And then we started messing with stuff that was inside of radicals, and we came up with another couple of facts that must be true about any x's that go into this function. So now all we got to do is keep in mind that all of these things must be true at the same time. Any x value that makes all of these things true is part of our domain. Okay, so we're going to combine all these things together into one single rule. Right now it's kind of 4 separate rules. And the way I'm going to do that is I'm going to create a big number line. So down at the bottom here, leave some space above this because you're going to want a little bit of room to write above this. And I'm going to look at kind of all the rules that I've written so far and pull out the important numbers. The smallest one appears to be -3. We also have 1 that appears, and then the biggest one is 2. And above this number line, I'm going to make some separate graphs, one for each of these things. Okay. So I'm going to kind of stack them on top of each other. This is the part that I was talking about before our friends left us for the assembly. I'm actually going to put those two together into a single graph. X can't be 1 and x can't be -3. You guys know what that graph looks like, right? It can't be 1 and it can't be -3. So that's the graph of x can't be 1 and x can't be -3. All right, and above that, I'm going to make a graph for this, x less than or equal to 2. So 2 is the key number here. It looks like it's a closed dot at 2. Less than would be this way. And then above that, I'm going to put my last little bit of information. We also may need to make sure that x is greater than or equal to -3. So greater than or equal to means solid dot, and greater than goes this way. Our overall domain is going to be where all 3 of those things are true at the same time. Any number that is covered by all 3 of these. So we're looking for where do all 3 of those line graphs intersect or overlap one another, okay? So let's start from the left. In this region over here are all 3 of the graphs covering the numbers in this region. We've got 2 of them are covering, but not the 3rd one. This is not part of our domain, okay? Let's look at the regions, and we'll come back and look at the in-between numbers in a moment. What about in this region between -3 and 1? Don't worry about at -3 and 1, but are we all overlapping in this region? I'd say we are, so this is going to be part of our domain. What about in between 1 and 2? Yes or no? Yes. What about from 2 to infinity? Are we all 3 overlapping? No. Okay, so all we need to do is figure out what happens at -3, at 1, and at 2. So look at -3. Is -3 a part of all 3 of these graphs? It is part of this blue one and this green one, but it is not part of this purple one. So since it's not part of one, it is not part of our domain. What about 1? Is 1 part of all 3 graphs? Nope. And what about 2? Is 2 part of all 3 graphs? It's inside of an interval here, it's inside of an interval here, and it's a solid dot here. Yes, it's part of all 3 of the graphs. So that's a solid dot. So there's our domain. It is -3 to 1, and 1 to 2, and 2 is included, but -3. Oh, yeah, thank you, sorry. Old school scroll. Yeah, I got you. I know what you mean. Scroll down, scroll up. Move the page so we can see what you're doing. Okay. So that was a big process. Are we feeling okay about the process? Yes. The key question in this class, though, is are we okay with understanding what we did and why we did it? Okay. So you're going to hear me circle back, and some of you are going to get annoyed with this, but this is what we need in order to use this tool throughout the rest of the year, because this is not going away. Day one, we'll be using this like at least 15 other times throughout the course of this year. So the idea here is I got a big complicated function. I'm going to focus on the pieces that I know can cause problems now. Right now, I'm only going to be throwing functions at you that have roots and fractions in it. Now, when we get into Unit 3, we're going to expand this because there's other things that can cause problems too. There's rules about logs, what can go inside of logs. So when we get to that, we'll be finding domain for those, and then we'll just have to look out for logs as well. And we'll have to remember the rule for logs, which is the same as the rule for square roots, except not equal to 0. We can't put a 0 inside of a log. It has to be strictly positive. Okay, but we'll do it the same way. The process will be the same. We'll look at the thing inside of the log, we'll write the restriction on it, we'll solve it. If we have multiple things going on, we just need to treat them all separately. Sometimes you're going to have a denominator that also has a square root in it. That's okay. Do the entire denominator as its own thing, and then come back and look at the square root as its own thing. If you have multiple restrictions, eventually you're going to have to find where all of them are true at the same time. For me, this is easiest to do visually by making a line graph of all of your different restrictions, stack them on top of each other, and then go through from left to right and look for where those overlaps are. All right, questions? Yes.
Sorry, just for the domain, it's true where not all of them overlap, but at least two of them overlap?
For that wonderful question. So the question is the domain where at least two of them overlap, or is it where all of them overlap? Can someone help me out with the answer to that? Nope, it's simpler than that, thankfully. I hate it when rules are like, sometimes it's this way and sometimes it's this way. This is a nice simple one. Everything has to be true. Everything. If we had 4 graphs stacked on top of each other and 3 of them were covered but one of them wasn't, we would throw it out. It wouldn't be part of the domain. Okay, so everything has to be true, meaning either it's covered by an interval bar like this, or it's a solid dot, right? Solid dots are included, but open dots are not. Okay, so this 2 ended up being included because there were no open dots and there were kind of no blank intervals. But -3 was not included because of that open dot. Excellent question, thank you for that. What other questions do you guys have? All right. Hey, I'm going to ask you, there's going to be several times throughout the year where there's something that's really simple. I need you to know it. Rather than spending time in class doing it, I'm just going to ask you to read it out of the textbook. So I'm going to ask you to do some self-study on boundedness and continuity. I have given you a little quiz at the bottom of the page. If you read through page 95 on boundedness, just the section on boundedness, and 90 to 92 on continuity, and you can answer these questions, then you're good to go. Okay, so look over the questions. I'm not sure, and I'll show you what the answers are, and you're like, I'm not sure why the answer to this is this, then I'll definitely explain it to you, okay? But rather than us spending 10 or 15 minutes in class, you can probably just look through it. Plus, I want you guys to get good at the skill of reading college level textbooks. We're going to be doing some more practice with that throughout the year too. We will finish up the rest of these notes on Wednesday next week for section 1.2. The assignment that's listed in Canvas is all due on Wednesday. There will be a separate assignment next Wednesday that covers the second half. You're going to hang on to the assignment that's due today and show me that with everything on Wednesday. How much time do we have here? Oh, lots of time. Look at us. 18 minutes left in class. I'm going to ask you guys to remain in the seats you're in right now. I'm going to go through and call roll. Give me just a second. And then make a seating chart, because it's going to help me learn your names. Okay? And then after that, you can move around. So